In this video, we look at differentiating the natural log function. Now there is just like, e to the x and 2 to the x power, a special little case for 2 to the x, but in this video, we will only look at natural log, not log with some other base, right? Because remember, log base e of x is another way of writing that is ln x. Okay, but if this e were 2, log base 2, then the derivative has an extra little step. Save that for another time. So, derivative of e to the x is simple e to the x. Derivative of natural log of x is 1 over x. Okay, another fairly easy derivative. And just like e to the x, the derivative of e to the u, we had a special little chain rule, eu du. Okay, same thing here. Look at this 1 over x, right? If it was anything else other than just an x, we make it a u, so that is pretty basic. So what's the du? That's the chain rule, right? Du times 1 over u is du over u. So I read it like that, du over u, because it's easy to memorize. Derivative natural log of u is du over u. So let's look at this first example in applying this formula. We don't just have an x, right? We have an x squared. So its derivative is du. So derivative of x squared is 2x over u. Okay, that's the u, right? The original thing. Du over u. And simplify it, we could reduce by an x. So we get 2 over x. All right. I want to show another approach for this one because we'll be reviewing the properties of natural logs, and one property is that if we take the natural log as something with an exponent, we could rewrite this as 2 ln x because the rule says we could bring that exponent down to the front. Okay, that's a property, the exponent property, or something like that, of natural logs. So now if we did derivative of this, we do only have ln x, right? Ln x. So that derivative is 1 over x, but we have this 2 out front, which is constant, so it stays. And then you could see 2 times 1 over x is 2 over x. We get the same exact thing. Okay, oftentimes with natural logs, you might use a trick and make it easier, and that's okay. That will come increasingly more important the uglier these problems get. I wanted to do this next one because this is a common mistake, thinking like ln can distribute. This is not the same as this. Okay, you cannot distribute natural log like that. It doesn't work. Remember, natural log, it's an operator, right? It's kind of like, think square root. If I did the square root of 9 minus 4, you can't distribute the square root to each and say square root of 9 minus square root of 4, right? It doesn't work. This side would be square root of 5. This would be 3 minus 2, which is 1. They're not equal. I know it's tempting because then the derivative of that is easy and the derivative of that is easy. It doesn't work. So it's all right. It's still easy. All of this is u. Right? And if it helps, you can write this on the side. U is 3x to the 4th minus x squared. So du, the derivative of that with respect to x, right? And I know I'm technically not writing du dx. It's a mnemonic. This helps memorize. So derivative of that is 12x to the 3rd minus 2x. So therefore, y prime, right, dy dx is du over u. 12x to the 3rd minus 2x over 3x to the 4th, the original, minus x squared. Notice as well the natural log is gone. When we do derivative, right, the formula, there's no more natural log. Now this thing could be cleaned up a bit. In fact, everything has an x, right? We could factor that out. Fully factoring it, we could pull out, 2x from each. So 2x. In the denominator, we could pull out x squared from each. Okay, and what are we left with? We're left with 6x squared minus 1, and we're left with 3x squared minus 1. So all that we can do is cancel one of these x's, right? So we get 2 6x squared minus 1 over x 3x squared minus 1. Doesn't simplify much, but we at least did get rid of an x. Okay. Next example. We do have properties of natural logarithms in which subtraction can yield division. But division, there's nothing we could do with this. I know it's tempting as well to like try to cancel these two ln's, but again, that's an operator that's like trying to cancel a square root with another square root. They don't cancel. We could maybe change this to product rule if we wrote the denominator with a -1 exponent. Usually if we have to use quotient rule, it's usually easier to just leave it alone. So let's do that. So f is ln x, f prime is 1 over x, g is ln 2x, g prime is, let's see, derivative of 2x is 2 over 2x, right? So we get 1 over x. This happens quite often. Even though it's not just an x, oftentimes the derivative will just come out to be 1 over x anyways. Okay? So, quotient rule, we have f prime g. So the derivative here, let's change colors. The derivative is f prime g. I kind of wrote it out of order here, but that's right. 1 over x times ln 2x minus fg prime, so fg prime ln x times 1 over x over g squared ln 2x squared. Well, not a whole lot we can do here. Well, I don't know. Let's see. We have both of these 1 over x's. We can factor that out first off. And then what we'd be left with is this ln 2x minus ln x. Here's where the property comes into play. The property of natural log says if we have subtraction, you could change that to, so ln 2x minus ln x becomes 1 natural log, and subtract changes to division. And the reason is because natural logs have to do with exponents, right? So naturally they have some rules like where division means subtraction and multiplying means addition. So anyways, all that simplifies to x's cancel ln 2. Now the denominator we cannot do anything with. Now in the first example I said we could bring down the exponent, but this, notice the squared is on this entire thing, the entire ln 2x, not just the x there. So we actually cannot do anything with that. The only other thing I'm seeing we could do is 1 over x. Right, that looks kind of weird being in the numerator like that. So the derivative, we'd move that x to the denominator, right? Because that's like 1 times the numerator, x times the denominator. And then in the numerator, we just have this ln 2. I'm not going to write 1 times the ln 2. I'm just going to change that to ln 2. Okay, that is the answer. Oftentimes, the derivative of these is really easy. It's the cleanup that gets to be a little tedious. Okay, last example. Wanted to end with at least an example of something we've looked at in the past. So this demand equation, the demand P, right, we often think of like price. Determine the marginal revenue. Remember, seeing that marginal means derivative. Revenue, so we have another formula, is x times P. Okay. So we need to find this revenue, x times that p that we have here, and then do derivative. So the revenue function is x multiplied by 45 over ln x. Okay, now it's derivative because we need marginal, right? Then we're going to need to do quotient rule. F is 45x, f prime is 45, g is ln x, g prime is 1 over x. So the derivative is f prime g, 45 ln x, minus fg prime, 45x times 1 over x, all over g squared ln x squared. Okay, let's clean this up. 45x times 1 over x, those can cancel. We could factor out a 45, I guess, so 45, and we'd be left with ln x minus 1 over ln x squared. So that's our marginal revenue, which I put MR right here, right? Marginal revenue. That's the marginal revenue function. And it says to compute it when x equals 20. So r prime, now let's change colors. R prime of 20. Substitute 20 in there, we get 45 times ln 20 minus 1 over ln 20 squared. And substitute all that in the calculator because I cannot, right? I don't know natural log of 20. Be careful, make sure you do natural log of 20 and then subtract 1. You know, some calculators will automatically give you an ln parenthesis. Okay, you want to end that parenthesis and then subtract 1. Otherwise, you do natural log of 19. Anyways, check your work, but in a calculator, you should get about 10, something pretty close to 10.